recorded now. Okay, so so we left off talking about dynamic equilibrium and this concept of equilibrium that is super important going into Chem 201, right? And that concept is that the rate of one process and the rate of another process, when they become equal, make a sort of steady state, right? So you can't measure any change in the pressure of the volume above the liquid or in the amount of liquid necessarily, right? But there's always these processes happening, right? So the evaporation and condensation never stop, right? They only come to this kind of steady state. Does that make sense, guys?
Yes.
Cool. Questions?
No.
Okay, cool. We also left off talking about concepts of evaporation and condensation, right? What is evaporation?
When water turns into a gas.
Right, but not just water, right? Any liquid going
Yeah.
from the phase to the gas phase, right?
Yeah.
And then condensation is?
When a gas turns into a liquid.
Exactly, right? So the opposite process. Is evaporation endothermic or exothermic?
It is endothermic, or just kidding. Wait. Yeah, no, endothermic.
Yeah, it's endothermic, but why?
Because the molecules of heat.
So going from a liquid to a gas, are the molecules getting more or less free in terms of motion?
More.
They're getting more free. Yeah, absolutely, right? In order to get more freedom of motion, right, they have to get more energy. If they have to be given more energy to have that extra motion, then that must be an endothermic process. Does that make sense, guys?
Yeah.
Cool. I don't think it's helpful to memorize these things at all. I really think that you need to understand it because otherwise it is super easy to get these wrong, right? Anytime you have these kind of binary concepts, it's super easy to flip them around in your brain if you don't understand what's going on, right? So we're always thinking about, are the molecules getting more or less free? Does that make sense?
So is condensation endothermic too, or is it the opposite?
It's the opposite, right? So condensation, we're going from a gas, which has a lot of freedom, right, to a liquid, which is less free, it's more restricted, right? So in order to make that transition from more freedom to less freedom, they had to give away some energy, right? Does that make sense?
Yes, thank you.
Yeah.
Any other questions about those processes? Okay. Cool beans. So this is one of the things that I'm guessing we didn't talk about in chapter 5. I think I might have drawn this maybe very poorly in chapter 5 when we were going over some problem solving, but this kind of method of collecting gas over water, right, by displacement of water, is a really common technique trying to collect a gas, right? And the reason why you can't collect a gas directly, you can't just put it into an empty tube, is because the tube isn't actually empty, right? What's inside of the tube or whatever container?
The gas.
Air, right? Does that make sense? So if you're trying to collect a pure gas, right? and you have a test tube that's just hanging out, right? And you put your little gas maker into the test tube with no liquid or anything in it, right? All you're doing is mixing up air and whatever gas you're making. Does that make sense?
Yeah.
You guys hear my daughter there? She's singing. Cool. So, did we talk about this in chapter 5? I feel like we did, but you guys are giving me the sense that we didn't.
It's not looking too familiar.
Anybody else? Okay. So, go back and kind of talk about gases for a second. So whenever you have a chemical reaction that's producing a gas, right? Like the problem that we just went over, when you're collecting that gas, right? It's not enough to just pipe that gas into some empty container, right? Because no containers are actually empty. What do they all contain? Talking about gas, there's always going to be air in that container, right? So if you pure gas, right, to make sure that there's no other gases in your container, right? So the way that you can do that is by filling up your container to the tippy top with water, right? And then having the gas displace the water. Does that make sense?
Yeah.
Everybody all right with me? This is a really, really important picture for understanding gas reaction and why we have to use that partial pressure of water when we're talking about collecting a gas over water, right? Questions? Anybody?
No, I'm okay.
All right. So the pressure exerted by a vapor when it's in dynamic equilibrium with a liquid is called the vapor pressure, right? So once we've finished collecting this gas, what's going to happen is we have our, let's say this was carbon dioxide, like from our example that we're talking about, right? There'd be carbon dioxide, majority of the gas particles in here, right? But there's going to be some other vapor molecules. What are they?
Would it be H2O as a gas?
Yeah, absolutely. It would be water vapor. Exactly, right? So just like when we were looking at this picture of water in a closed container here, right? We know all of the water is not in the liquid phase. Some of it is a vapor that's hanging out above the surface of the liquid, right? So the same is true for our test tube here. Does that make sense, guys?
Yeah.
So the amount of water that's present in my sample of gas that I'm collecting is proportional to the vapor pressure, okay? Which is essentially the same thing as talking about the partial pressure of water at a particular temperature. Does that make sense?
Yeah.
Anybody else want to chime in here? How you feeling with this, guys? You guys see how the narrative is starting to come together with all of the chapters at once?
Yeah, kinda. Yeah.
Anybody have questions about this? So the vapor pressure is just another way of thinking about partial pressures, right? Specifically, the vapor pressure at a given temperature is always going to be at dynamic equilibrium, right? Again, dynamic equilibrium assumes that the conditions under which that gas exists are not changing, right? Or not significantly changing. Does that make sense? So not drastically changing temperatures, pressures, volumes, anything like that. Cool.
Sure.
Cool. So the higher vapor pressure, the more volatile the liquid, right? So the higher the partial pressure of a gas is at a particular temperature, the more volatile the liquid, right? What did we say that volatility was connected to in terms of intermolecular forces? Stronger or weaker? So if you're more volatile, do you have stronger or weaker intermolecular forces?
You said if you're stronger volatile, is it stronger or weaker forces?
So if you have a more volatile liquid,
Mm-hmm.
the intermolecular forces in that liquid stronger or weaker?
Weaker?
Weaker, absolutely. Is everybody comfortable with that?
Yeah.
Questions about vapor pressure? So this is just kind of taking what we talked about in chapter 5 with these partial pressures and putting it into a new context, right? Cool. So if the volume of a chamber is increased, right, it will decrease the pressure of the vapor inside the chamber. At that point, fewer molecules, fewer vapor molecules in a given volume. And so the rate of condensation, meaning going back to the liquid, is going to be reduced, right? So for a period of time, the rate of vaporization will be faster than condensation, which is just a fancy way of saying you're gonna make more vapor, right? So if you increase the volume of a container, you decrease the pressure, right? Because remember, pressure and volume are inversely related. So if you increase the volume, you decrease the pressure, and what'll happen is the number of molecules in the gas phase start to rise to correct that balance, right? And it'll correct until you reestablish this equilibrium. So here's a picture of what we're talking about here. So let's say you started off at this volume, you'll get to some kind of dynamic equilibrium. If you increase the volume, right, now you're going to increase the number of molecules that can be in this space, right? And same is true the other way around. So if you were to decrease the volume, now you're going to increase the condensation, right? Which is going to mean less molecules. Does that make sense, guys?
So there's more molecules if it's the volume's increased and less if it's decreased.
Exactly. Yeah. And that's because of this relationship between volume and pressure. So as the volume increases, the pressure decreases, right? And so then the number of moles that are in the gas phase are going to try and increase. Right? Does that make sense?
Yeah.
Okay. One of the really important parts or concepts to dynamic equilibrium is that anytime you disturb equilibrium or alter a system that's in equilibrium, the system will always try and respond to come back to equilibrium, right? So this idea that nature always wants to be in a steady state and will always try to get to that steady state is essentially another way of stating that right? You can think about this dynamic equilibrium as being the energy state. More energy.
I think your volume kind of went out.
Yeah. So when you're talking about dynamic equilibrium, right? Your dynamic equilibrium is essentially your lowest energy state, right? anytime you change the system, like say by increasing the volume, okay, you are going to force the system to re-equilibrate to come back to that dynamic equilibrium, right? So the change in this particular case is that we have the rate of vaporization, right? But at some point, that rate of vaporization will stop increasing, and the rate of vaporization and condensation are going to go back to equilibrium, right? But it'll always change to right the ship, right? To get back to that lowest energy state. Does that make sense?
Yeah.
Cool. So understanding that the will always shift to get back to equilibrium, that concept is related to the Chem principle. You guys will get into that in great detail in Chem 2. Increase in temperature, increase the number of molecules able to escape from a liquid. I think that's pretty intuitive, right? As the temperature increases, the pressure also increases, and so you make more molecules able to go into the vapor phase, right? Specifically because gases are so susceptible to changes in temperature and pressure compared to their condensed phase friends. Changes that you see with small changes in temperature will result in large changes to vapor pressure. Does that make sense?
Yeah.
Cool. Especially in the case that you have low intermolecular forces, aka a volatile liquid. So the more volatile your liquid is, the more sensitive to changes in temperature it's going to be, right? Cool. So this is a graph of vapor pressure as a function of temperature. This is a kind of graph that I love to use on tests and quizzes because it holds so much information. Okay, so let's talk about what. So this is the slope tells you about.
Monica, it's like so hard to hear. I like hear a man talking in the background.
Yeah, there's a lot of background noise.
Cool. So Teddy, if you just want to mute while we're in between things, perfect. Thank you. So I know it's annoying to have to go back and forth between the mute button. Okay, so what we're looking at here in this graph is essentially the strength of intermolecular forces. Okay, so the higher the slope of this vapor pressure curve, the steeper the slope, the weaker the intermolecular forces are, right? So looking at diethyl ether, right, the vapor pressure of this liquid grows much more steeply as a function of temperature, right? That tells us that the diethyl ether has less intermolecular forces than, say, something like water, right? Water is still susceptible to changes in vapor pressure as a function of temperature, but it changes more slowly, right? Implying that water has more intermolecular forces or stronger intermolecular forces, right? Is everybody cool with me on that?
Yeah.
Yeah.
Cool. So looking at this graph, which one of the molecules represented here has the strongest intermolecular forces?
Would it be the ethylene glycol?
Yeah, absolutely. It would be ethylene glycol, right? Is everybody comfortable with that? Because that's definitely the kind of question that I would ask on a quiz or a test. So again, just to restate, the vapor pressure as a function of temperature tells you about how volatile a liquid is, right? So looking at ethyl alcohol, aka ethanol, compared to water, right, is much more susceptible to changes in vapor pressure as a function of temperature because it has less intermolecular forces. Cool.
So basically a lower vapor pressure and lower temperature makes it a lower IMF?
Lower vapor pressure at a lower temperature, yes. Mm-hmm.
Okay, thank you.
Yeah, so this is all kind of relating what we were talking about last time, right? So we said the boiling point and the melting point is also a function of those intermolecular forces, right? So now we're saying that the vapor pressure, the amount of the liquid that will be converted into a gas at a given temperature, is also a function of breaking apart those molecules, right? And that's a function of intermolecular forces.
So if like the question was what has the highest IMF, would it be diethyl ether?
No, it would be the opposite, right? So diethyl ether would have the weakest intermolecular forces, right? Because essentially
Oh,
what the curve is showing you is that you don't have to put in very much energy to get diethyl ether to vaporize, right? So you see the vapor pressure, as the vapor pressure increases, the number of molecules in the vapor phase are also increasing. Does that make sense? Those two things are proportional.
so ethylene glycol has a stronger IMF?
Yes. So the
Okay,
IMF of any of the things pictured here would be ethylene glycol, right? Then water, right? Then ethyl alcohol, then diethyl ether.
okay. Sorry, I got it mixed up.
That's okay. That's okay. This is it's, again, when you're talking about these kinds of binary concepts, there's a lot of moving parts here, right? And it's very easy to get these things inverted in your mind, right? So I think the picture is really helpful in terms of figuring out what's going on here. When you look at like this kind of picture, right? So increasing the temperature is making more molecules go into the vapor phase, right? So that's what's happening here, right? As you increase the temperature, more molecules are going into the vapor phase. How many molecules go into the vapor phase depends on how attracted those molecules are to each other in the liquid phase. Does that make sense?
Yeah.
Lowest slope, strongest intermolecular forces. Coolsies?
Yes.
And we talked about weakest, highest slope, weakest intermolecular forces. Cool. So now we're going to start talking about phase diagrams. So phase diagram is going to show you all of the different types of transitions that a substance can make, right? Specifically, this one given is for water. So if we're looking at the solid form here of water, that would be ice. This is the liquid form, aka water, and then water vapor is our gas state, right? So a phase diagram, the lines here are representing the separation of two distinct phases, right? So as we cross this line between ice and water, right? We're going from ice to water, that's melting. What was the stupid word that we have for melting? The technical name?
Fusion.
Fusion, that's right. If we're going the other direction, crossing from water to ice, right? That would be freezing, aka crystallization. Does that make sense, guys?
Yeah.
So we call this the fusion curve, I believe. You don't necessarily need to know that, but just understanding that going from solid to liquid is melting, going from liquid to solid is freezing or crystallization. This line here is representing the transition from liquid to a gas, right? So going from the liquid to the gas is the vaporization, and back the other way is condensation. And then here, going from the solid to the vapor phase directly gets you sublimation, and the opposite of that takes you to deposition, right? We talked about all of these last time, right? Briefly.
Yeah.
Cool. We call this the sublimation curve, I believe, and then this is the vaporization curve, okay? Again, that's kind of trivia, but just so you guys know when you're looking through the textbook what they're talking about. A couple of other important points to talk about. The triple point here is the point at which all three phases exist at the same time, right? This particular temperature and pressure are obviously really hard to maintain, right? So this isn't a common place for substances to exist, right? The other place to point out is this critical point. The critical point is the point after which you can no longer distinguish between the vapor phase and the liquid phase, right? And so what you end up with above this critical pressure and temperature is what's called a supercritical fluid, right? It looks and behaves both like a liquid and like a gas. We won't get too much into those, but it's a pretty fascinating area. If you guys are into materials especially, it's pretty neat. Any questions about what's being related here? We all right?
Yeah.
You guys wondering what the heck the point of learning this is?
Yeah.
Cool, that's perfect. So why would it be important to know this relationship between pressure and temperature and phase changes?
For lab.
Yeah, absolutely. For practical purposes, right? So it's kind of a hard thing to talk about in the abstract because it doesn't seem very important. But when you're talking about this relationship between pressure and temperature, it can tell you what phase you can expect a substance to be in, right? So we know at, where are we here, is 0 degrees Celsius and 1 atmosphere, right? That this is the freezing point of water. Everybody with me there?
Yeah.
And then over from 1 ATM to 100 degrees, that's the point at which you go to a vapor, right? So it may not seem like a very important thing, but being able to navigate these kinds of phase diagrams for different substances is really important. This is probably the simplest kind of phase diagram that you would see. A lot of other phase diagrams will have, especially in the solid area, multiple crystal versions of this, right? So, and even this one, ice actually has, I think, 9 different ways of crystallizing. So this is a much more oversimplified version, but if you know what pressure and what temperature you're freezing at, or when you're crossing from one of these barriers, you can actually make different crystals of ice form. So, it doesn't seem like super important for you guys, but when you get into solids, especially like solid state chemistry, the crystal structure that you make something in is going to determine all kinds of properties like thermal conductance, kind of heat capacity you might have, stuff like that, which is super important when you're designing things for electronics or computers or anything like that, right? So this is more of an engineering type of application, but it's a really important one, right? Does that make sense? Are you guys understanding what you might need to do with a problem like this? So let's say I asked you on a phase diagram that wasn't water, what at pressure of 1 atmosphere, what temperature is required to vaporize this liquid, right? In this particular case, what would the answer be? At 1 atmosphere, what's the temperature at which water will vaporize?
100.
0 degrees Celsius.
Vaporize.
100.
100. Is everybody comfortable with that? So again, these are things you already know for water, but being able to navigate that information for any substance is what I want you to get out of this phase diagram talk. Cool? It's kind of hard to talk about without seeing more.
Cool.
We'll talk about more examples later. There's one other really important thing that I want to point out to you guys here, and that's the slope of the fusion curve here is negative. Do you guys know what I mean by that? So if a slope is negative, it's going in this direction. If it's positive, it's going in this direction, right? You guys with me?
Yeah.
Cool. So having a negative slope for your fusion curve tells you that the density of the solid phase is less than the density of the liquid phase, right? So we know that intuitively about water because when we put ice into water, what happens?
It floats.
It floats, exactly, right? Ice floats in water because it's less dense, right? So that's another piece of information that you can get just by looking at this phase diagram, is that the density of solid water is less than the density of water, right? And that's pretty uncommon in nature, right? Generally speaking, most solids are more dense than their liquids, right? Yeah?
Yeah.
Okay, so where the heck did we get all of this information from? So the heating curve of a liquid is giving us the information relating the temperature change and the amount of energy that's being added, right? So if we are adding energy to water, for example, the energy that we're adding will go to changing the temperature up to a certain point, right? When you get to 100 degrees Celsius, the heat is no longer changing the temperature, right? Now it's changing the phase. Does that make sense? And that's where you get this flattening of the curve right here. Is everybody all right with that?
Yeah.
Yeah.
So what this flattening of the curve relates to in terms of this graph is this vaporization curve, right? So all of that flat point is this vapor curve, right? That's all the points at which the temperature is no longer changing. Here, the temperature and the pressure are both allowed to fluctuate, right? In this case, we're keeping the pressure constant, and that's why the temperature is not changing. Are you guys picking up what I'm laying down?
Yes.
Cool. Cool. So if we're keeping things at a constant pressure, then when we get to that boiling point, right, now all of the heat that's being added is going towards a phase transition, not changing the temperature. If you were to change the pressure at which this graph was being done by, say, doing the same experiment at the top of Mount Everest, for example, what's going to happen to the boiling point? So as you go up in elevation, what happens to the pressure?
It lowers.
Yeah, exactly. It decreases, right? So as you go up in altitude, your pressure decreases. As your pressure decreases, what happens to the temperature? Do they change together or are they opposites?
They change together.
They change together, exactly, right? So as you decrease the pressure in the atmosphere, you'll also decrease the boiling point of a liquid, right? And that's why I believe the boiling point of water, I think it's like 5,000 feet. I'm pulling numbers out of the top of my head, but it's something like 79 degrees at the top of Mount Everest, I think. I have to double check that, but yeah. So pretty dramatic changes. Cool. So when the temperature of liquid reaches the point where the vapor pressure is the same as the external pressure, vapor bubbles will start to form anywhere in the liquid, not just at the surface, right? This phenomenon is called boiling, and the temperature at which something boils is called the boiling point. Everybody all right with me there?
Yeah.
Cool. Oh, here we go. So boiling point at the top of Mount Everest, the partial pressure is 0.32 atmospheres, and it's a 78-degree boiling point. Sea level, it's 100. Mile high, so this would be like Idlewild, Big Bear, I think are right around that mile high altitude. So your boiling point changes of water. That's why do any of you guys spend time in the mountains or at higher altitudes ever?
I've been to Idlewild.
Okay. So if you ever try and bake in those places, all of your recipes have to change because of this small change in pressure. So if like you're trying to bake bread or cupcakes, anything like that, even cookies, you have to alter your recipes because of this. So that's kind of little trivia for you. But if you ever try and make cookies at higher altitudes and it doesn't work, then that's probably why.
Is that going to be on the quiz?
No, that's trivia. So, okay, so we talked about this supercritical temperature and pressure, right? That's the point on your phase diagram where you reach that supercritical fluid. And here is an example of going from this gas-liquid divide here, where you can see the liquid is starting to vaporize a little bit. And then you can see an increase in temperature is making the liquid more volatile, up until you get to a point where there's no more phase separation, right? And again, we call it a supercritical fluid because it has properties of a liquid and a gas. Coolsies? So we kind of already talked about these things too, so I'm going to go through it pretty quickly. But again, we have these opposite processes of sublimation and deposition, right? Going from a solid to the gas is the sublimation. Is that going to be endothermic or exothermic? This is going to be a yes for sure. It's going to be endothermic.
Endothermic, right? Okay.
Yeah, exactly. So going from a solid to a gas, right? The molecules have to get more freedom, right? Which means that we have to add energy. We have to add energy to the system. That's endothermic, right? And then deposition would, of course, be exothermic, exactly. Oops. So this is I really like GIFs, you guys, because they give you a sense of what's going on. So this is a GIF of sublimation happening. I think most people have seen sublimation in the form of dry ice before. It's less common to see the opposite process, which is deposition, right? But I think it's a little bit easier to intuitively understand how a gas could form a solid than the other way around. This kind of feels less natural. But cute pictures anyways. Oops. So this is an example of where deposition might be used. So when you're looking at making certain materials, a lot of the times making them one layer of molecules at a time is important in getting the right crystal structure. And so this deposition method is really common in material chemistry. So as a solid is heated, its temperature rises and the molecules vibrate more vigorously. Once the temperature reaches the melting point, the molecules have sufficient energy to overcome the attractions that hold them in position, and so the solid melts. Melting is freezing, the opposite of melting is freezing, right? So freezing and melting are also opposite processes. This is a couple of GIFs of recrystallization, which if you guys go on to organic chemistry, you're gonna see this is probably some of the cutest chemistry that we do. You guys can see these crystals, solids forming in the base of these containers. Isn't it so cute? I love it. You guys are like, whatever, I don't care about that. Cool, good talk. Okay, that's recrystallization. So this would be forming solids from their aqueous components, right? So basically making a solid form from an aqueous solution. Beep, boop, beep, bop. This is just looking at the same kind of concept, but with the melting instead of the boiling point. So that flat space on the curve is, again, when your heat that you're adding starts going from changing the temperature to changing the phase. And that's represented in the fusion curve, right? Beep, beep, beep. So the enthalpy of fusion and crystallization are opposites, right? So we talked about the enthalpy of vaporization and the enthalpy of condensation. We said that they are equal and opposite. The same is true for these relationships, crystallization and fusion, or AKA freezing and melting. Does that make sense? So the energy that you get by sticking these guys into this solid crystalline lattice is the same energy that would be required to get them to melt. Cool?
Yeah.
So this is putting all of that together. And then we kind of talked about all the different points of the phase diagram already. I think it's easier to understand why we talk about all this if you understand that we're just building this phase diagram, right? So all of the things that we just talked about were just the ways in which we build a phase diagram. Does that make sense for you guys?
Yeah.
Cool. And so again, this is the kind of navigation that you're going to need to know how to do for a phase diagram. So if you're looking at, like, say line A, right? At what temperature does this transition happen? Something like that, right? And we'll talk about more specific examples. And seeing some different substances. So the phase diagram of iodine, again, this fusion curve, right, has a positive slope. What does that tell you? So what did the negative slope of the fusion curve in water tell you? That the solid is less dense than the liquid. Well, yes, in this case, the solid is more dense, right? In the case of water, it's the opposite. When the fusion curve is negative, then the solid is less dense than the liquid. If the fusion, if the fusion curve is positive, right, like this one is, then that would be an instance where your solid is more dense than the liquid. Does that make sense, guys? How are we doing?
So a negative slope is less density.
Negative slope means the solid is less dense than the liquid. And we will talk about all of this, not today.